starting to work now. Yeah, now we can see it.
Okay. So thank you. I am going to make the assumption, perhaps not fully correct, that most of you have seen, the talk, or at least know about the helicopter enough, so I don't have to cover a lot of ground as in the way of introduction. I thought I would just talk more about, some of the things that have happened since last year. We're on our way to Mars. The helicopter is healthy. Its battery is getting charged every couple of weeks. So we're all looking forward to that mission. And I thought I'd give you guys an update on what's been happening since approximately about last year. And also give you a little bit of direction, sense of what's maybe coming after the Ingenuity system, demonstrates rotorcraft flight on Mars. I'm going to attempt to show a short video clip, which is basically the mission profile on Mars. It has audio. I'm hoping that will come through.
Sometimes you have to do something just to show that you can do it. When the Wright brothers flew for the first time, they flew an experimental aircraft. And in the same way, the Mars helicopter is designed to show that we can fly powered helicopter flight in the Martian atmosphere.
From day one, this was the unwavering dream of our team, to get our helicopter launched to Mars so that we can get that opportunity to do that very first rotorcraft flight test in the actual environment of Mars. It's extremely difficult to fly at Mars because the atmosphere is so thin. Compared to Earth, at Mars it's less than 1%. So the first and foremost challenge is to make a vehicle that's light enough to be lifted. And then the second is to generate lift. The rotor system has just been very fast. 2,000, 2,200, 2,400, 2,600. We're spinning between 2,000 and 3,000 revolutions per minute, and it takes a lot of energy. So it's that balance of a very light system, yet having enough energy that's needed to spin the rotor so fast to lift, and on top of it, having to design in the autonomy.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
Our experiment window is 30 Martian days. So we have planned up to 5 flights of incremental difficulty.
The very first flight, the main thing is we want to get the legs off the ground, and so we will basically go up about 3 meters, and we'll hover there, and then we'll come down again. And that will be the first, really major milestone.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out, 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
At this point, we've tested all we can on Earth. We have mathematical models that shows how it will fly at Mars, and we've tested it in the simulated environment that we can create on Earth. It really is time now to do the real flight test at Mars.
Nothing is a given, but we have done everything we can in terms of a test program here on Earth. The vehicle's performing extremely well so far. It's been doing exactly the right thing, even right now when it's bolted onto the Perseverance rover. So there's a very good chance that we'll pull it off, yes. But it's still high risk, and none of us forget that you could have a glitch that, could mean end of mission, yes.
It's going to be exciting, reacting to any surprises we have. We can't wait. What's really most important is everything we're learning here is for the future rotorcraft systems that we want to introduce into space exploration.
Okay, perfect. I hope that came through well. So that's the helicopter that's on its way to Mars. It's on its stand, all done, all complete. It's what we call as the flight model, the FM. Just a little bit of a reminder for why are we interested in helicopters? I see it as sort of the 3 R's. The ability for a helicopter to reach places which you can't go with landers and rovers. The tremendous range that these systems can bring to bear for exploration, the next generation that we are looking at actively right now will have forward velocities in the 20 to 30 meters per second. So that can cover a lot of territory in flights ranging for many, many minutes. And then, of course, the fact that you can get up close and get high resolution images, and other instruments also can operate at high resolution. So that's kind of the main motivation. And this demonstrator, much like Sojourner, we hope paves the way for a generation of aerial vehicles on Mars. Mission concepts in a nutshell: there are concepts where we have it paired with a rover or a lander. One can easily imagine missions where there are more sophisticated instruments on a lander, and the helicopter acts like, goes back, brings back samples, those kinds of things back to a lander. There's also larger vehicles in the 20 to 30 kilogram class, carrying, 3-4 kilograms of science payloads that could be independent explorers, providing sort of planet-wide access to all kinds of terrain. So that's kind of the vision for the future. So what have we built? We have built Ingenuity. It's 1.21 meters from tip to tip. We came in at 1.8 kilograms. It's fully autonomous, and during our 30-day mission, we plan up to 5 flights. And not going very high, not going very far, to about altitudes of about 10 meters. So that's kind of like the plan. So let me just give you a little bit of a sense of some of the final tests that we were achieving. So here is flight testing, where obviously we are set up in our 25-foot chamber at JPL. It's about 25 feet diameter and about 80 feet high. And it's where we pump down to vacuum, backfill with carbon dioxide to mimic the Mars atmosphere, and we test. Now, one obvious factor that we cannot include in that testing is to change the gravity. So we have this gravity compensation system, which basically is a very fancy constant force tether line, which is mounted up high up in the ceiling, and this exactly compensates for the weight. And we model the flight dynamics effects of having such a constant tether gravity compensation system, and then the final flight dynamics, we validate that it's acceptable for flights on Mars. So that's kind of a gravity compensation system that got used. A lot of interesting safety not related technology in there. You'd be surprised, to make sure that it doesn't, literally the whole program is hanging by a string there when we fly that. Another bit of testing that we did is we have a solar panel on the top that is used to harvest the sun's energy. So one of the nice things about the JPL 25-foot chamber is that it has the ability to simulate solar illumination all the way from Venusian orbits to, definitely to Mars. There are all these high power lights in the basement, which shine up through a window into a mirror, and then the mirror collimates the light down onto the bottom. And there's our flight unit with the solar panel being tested under solar illumination conditions, because that's how we'll be getting our energy on Mars. The other big test program that happened was to actually fully integrate with the rover and then deploy. So here, the chamber is under cold conditions. And there was a week-long test campaign that the rover folks did, and we were part of it. And towards the end, we went through a full deployment sequence from the bottom of the rover at temperature under Mars conditions, and that was very successful. And so we have every confidence that after the rover team finds a location for us on Mars, probably about 60 sols, the 60 Martian days after they land, we will be deposited onto the surface, and then, as the video showed, they drive away to a safe distance of about 100 meters, and they'll watch our first flight. So that's a deployment testing that we went through. Some other nice photographs on the Rotor launch. Here is the flight unit being delivered to the spacecraft assembly facility, and everybody's there in clean suits, maintaining both planetary protection and contamination control cleanliness. So they took delivery of the system, and then they are installing it onto the belly pan of the rover. So this is actually the belly of the rover, and the helicopter is being assembled onto the belly, and the rover is turned upside down to expose its belly, and then this panel with the helicopter is, attached onto the rover, and that's what's happening out here. You can see that the legs, all of the blades, the belly, and this is the rover upside down, and technicians are, engineers are assembling it on. That's a nice picture of after the rover's being turned right side up again. You can see where we are. That's where we are. You can see the solar panel. You can see the blades going out from tip to tip. And then we fly to Mars in a sideways position with effectively a debris shield surrounding us. It looks like a big guitar case. It's not shown in these photographs. And the reason we have a debris shield is that during the powered flight landing of the rover with the sky crane, there's a fair amount of rock, debris, and pebbles and things that are kicked up from the surface, and that protects us. So we are installed here with sort of a debris shield that's put on top of this. Then after we land, this whole system in the deployment process makes us vertical, and then we get deposited onto the surface. Then we had the actual launch, a successful launch, and we were very happy when we attempted to wake the helicopter up a few days after launch. It responded, and since then we have a very slow battery leakage from the avionics that's alive on the helicopter. It's in a very low power, sort of a hibernation mode right now. But nevertheless, every 2 weeks, we give it a little bit of a battery charge activity. And we have done, I believe, 6 of those charge activities so far. We're almost at the halfway point to Mars, and we've got a few more months to go. February 18th is the landing date. And it'll continue to be charged by the rover till deployment. And then once the rover clears our solar panel and we see the sun, we begin to charge ourselves. It's going to be a busy month at Mars. This is sort of the notional, you could imagine this as perhaps being flight 5, where we take off and go very far. Maybe even try to see whether we post-process images that we take from the helicopter to detect a separate landing site. Our normal landing site is something that, again, in the interest of being a tech demo, it's a very carefully surveyed site, surveyed by the rover cameras. So we make sure that it's acceptable in terms of being flat, not too many rocks, basically to guarantee, the least possible risk to the helicopter. And that's where we'll be taking and landing off on almost all our flights. But towards the end, we might get a bit sporty and see whether we want to go and land somewhere else. So while all of this has been happening, we have also been looking at more advanced designs. The thinking is that there is a whole class of science missions that would be possible given the unique mobility capabilities of a helicopter. And so there is a sort of 2 classes of designs that we are looking at. We are looking at essentially stretch versions of this 1.8 kilogram system that could go into the 20 kilogram to 30 kilogram class. And we are looking at both the coaxial design, which is the one that we ended up with for Ingenuity, primarily because of space constraints more than anything else. But since we would have had fully validated models on designing such systems, we're also considering a hexacopter type of system. Both these systems have significant payload capabilities. They have ranges easily in the kilometer class, and they have simultaneously the ability to hover and do standoff signs. And this hover time and the range can be traded off, so depending on the particular mission profile. The other sort of very high heritage version of Ingenuity, which we're working on, is what we're calling as the advanced tech demo design. And that's basically, we had taken a lot of very conservative steps in the design of Ingenuity. And especially after a successful test flights on Mars, we can relax a number of those things. And we believe with some improvements in the airfoil design, increasing the allowable tip mark numbers, and so forth, we can actually get to a system that could carry a payload of about 1 kilogram, which by itself may not be that interesting, but definitely something of this size paired with a lander, which has more sophisticated assets, is something that is a possibility for a future mission. Now, all of this has been captured, including a number of mission variants, into a white paper that was, put together by an extended team at JPL and across the country, actually, as part of the decadal white paper process. And so I would encourage those of you who are interested in looking at, what are all the science capabilities that future helicopters might bring to the table, to go and read the decadal paper, Mars Helicopter. So some of the science themes that are clearly enabled by such systems, and which are described in much more detail in the white paper, is everything from sort of the classic geological kinds of things, sedimentology, stratigraphy, a lot of interest in polar and mid-latitude sites where there are exposed ice scarps and volatiles, being able to get up close to them. There also is a role for profiling things in the boundary layer, looking at chemical composition. So essentially everybody who does atmospheric science could benefit from such a platform. But to me personally, the exciting ones are all related to astrobiology. We can probably get to places which are of astrobiological things. The stuff on geophysics, the range and mobility of this platform lets you to do a lot of wide area magnetic sensing, for example, for crustal magnetic field measurements. So that's an area with geophysics. And then the other thing that I think we think is particularly useful for these are small vehicles. We believe we can get them sterilized and cleaned enough to actually go and explore some sensitive regions without any risk of contamination, if you will. So that's kind of the possibility. So all of these, along with some representative mission profiles and mission concepts, are in the white paper, and we are actively working across this, both at JPL and with our other NASA and industrial partners, to advance the system. The idea being that if we have a successful summer with our test flight program, then these are all the things that we can bring to the table for future missions and see what gets traction from the larger community. With that, I wanted to leave time for questions, and so I will take questions at this time.
Hello, Mr. Balaram. Sorry about that. This is Lucinda Offer. How are you?
Good.
I have a question for you. Thank you so much for your presentation. Ingenuity is so exciting. Someone wants to know here, would you like to fly a balloon on a future Mars missions? And what are the advantages or disadvantages of helicopters versus balloons on Mars?
Right. So in fact, many years ago, there was a major Mars balloon study that we looked at. And in fact, I believe the French even have a balloon sitting in a warehouse that they never managed to launch because of some problems with the inflation system. So there are some engineering challenges related to balloon inflation, balloon films, long duration, so forth. But I think the biggest advantage that a rotorcraft system has is sort of the precision of being able to maneuver to exactly the point you want to. We're not at mercy so much against the atmospheric winds. And so we can get up close and personal to a lot of interesting features on Mars, which balloons by and large have had issues where they're subject to sort of fighting the wind a lot and not having that degree of control authority to sort of necessarily stay in place. Not to say it can't be done. I mean, it's one of those things where if you put enough engineering into it, the balloon system can also be done. But inflation and deployment of a balloon system is a highly non-trivial exercise, as the French found out in their balloon project from for the 1990s. And I think that would still continue to be a challenge.
Hello, this is Carrie Fay, and I have your next question. This is asked by Carlos Glender. Given the high RPM of rotor blades, 2,500 to 300 RPM, and the high propensity of sand on Mars, is there a concern about rotor blade erosion?
Yeah, that's one of the things we will find. Now, the rotor flow is basically taking air from above the helicopter and pushing it down. Our modeling to date indicates that we do not set up any significant recirculation of the dust and soil within the system. And soon as we achieve our target RPM, we very quickly change the blade pitch and we pop up quite quickly. And once we get to about 1 rotor diameter above the surface, the dust impingement issues are all quite minor. But yes, it's something that one of the reasons we're going to Mars is to see exactly what all of those phenomena are and how they impact us. But the current thinking is that we really don't expect to have much of an impingement from anything that we stir up.
Okay, I'm going to ask you the next question, and I didn't mean to turn my camera off. Can I do that? So, we recently saw an avalanche happen on Mars. So we've got Priya here. They're interested to know if you're going to sample that the helicopter might take a look at, maybe some of the Martian slopes, those seasonal flows that happen.
Right. So, not this helicopter. This helicopter's sole job is to provide engineering data so that we can validate and be ready for the next generation, the design of the next generation systems. So we actually are learning how to operate the system. We have learned how to test these systems. That was all, kind of writing the book on that, because that was all path-breaking work. But yes, the future systems, again, with the ability to do extended hover, extended close-up proximity operations, are definitely things like the recursive slope lineae, the RSLs, and other things. Those, whether they are of biological interest or not, I think the sentiment in the community goes up and down on that one, but definitely ice scarps, RSLs are all places where we can send such systems, both for sort of standoff imaging, as well as even we've been looking at some standoff sampling types of systems that can actually retrieve certain samples under those conditions. So definitely those are in the mission architectures and mission concepts for future helicopters.
Hi, your next question is from Andy Ware. If everything goes well with the current mission goals, does the copter have the potential to do more? For example, number of flights, distance? Yeah, so the ground rules that we have is that we get everything done in 30 sols, 30 Martian days after we get deployed. The whole Perseverance team and the agency has been incredibly, gracious in giving us those precious 30 days out of their very exciting, science campaign, and we don't want to be in the way of absolutely, getting in the way of continuing with the rest of the mission. So we get deployed early in the phase, where just after the initial commissioning, and so we'll likely, in some sense, be right part of their transition to their full mission. But we have no plans on doing anything beyond our 30 sols.
So I have a question for you. She's a 13-year-old, and she wants to be an engineer. And she's curious to know, how long will Ingenuity continue to work without humans on Mars to maintain it?
We, as I said, the 30-day mark, the experiment ends, and the rover will go off to do its very exciting science of getting samples ready to bring back to Earth. So it's very much like the Sojourner model, that you had back in the 1990s. That was a little, microwave box size thing, and it did a short mission, but it paved the way for spirit and opportunity, and curiosity and perseverance. So in the very similar way, this is a very definite objective and a very definite lifetime. And so I should also point out that from an engineering sense, we have used a fair number of commercial parts, and none of them have been, stress tested, if you will, to see if they last, 3 times, a long mission. So we are not designed for very long life. Also, Ingenuity in particular will not be able to harvest enough energy in the winter months to sort of keep itself, alive and so forth. So it's a very targeted kind of tech demo, which is really designed for the particulars of this experimental window we are in.
Thank you so much. Your next question comes from Michael Bushrow. In reference to your main work, is there any success in increasing the upper limit on lander mass due to EDL into a thin atmosphere?
Well, I think I'm not sure there's any relationship between the helicopter work and EDL. EDL has, is a separate problem, which I worked on for many years before I started working on the helicopter. There are, high LOD vehicle designs, which are, but would be a departure from the 70-degree half cone systems that we've been using for our payloads. And definitely, if you want to go into the multiple ton delivery of cargo and humans to Mars, you go more with those mid-LOD, lift-to-drag, sort of more gliding type vehicles rather than a ballistic entry type of blunt cone that we have. So there's very active work at NASA and other places on those kinds of systems. And so people are actively doing it, but I don't think anything in the helicopter world necessarily pertains to that. We are more of a asset of what you do once you get there, whether you're a scout for a science mission or whether a future astronaut uses these drones, much like people use them here on Earth to, survey or scout out or pick an optimum route or decide which place to go to. That would be the role for these systems, not so much to inform the next generation of EDL.
Just waiting for a cue to see if I would like to ask you one more question, if that's okay. I'm going to go ahead because I'm I worked in NASA Ames from Silicon Valley, and we had dirigibles there. And this will be the last question. We have our next speaker coming up, but William Hale asked an interesting question. Any plans for dirigibles? I know that takes us away from the copter, but it's a great question.
Well, I think if I understand you dirigible as being a tethered balloon platform, I think you have the same issues. It's tied to one place. You have inflation and deployment under either entry, descent, landing conditions, which are quite uncertain in terms of you don't really know what the atmosphere is doing when you try to inflate on your way down. Or even on the surface, inflating on the surface is non-trivial. And then you have the lifetime. You have to have materials which are sort of don't leak as much. So it's the same situation as with the balloons in the past. I think we have looked at them. I'm not to say they can't be made to work, and they may have a role in future Mars exploration too. It's just that for very specific point-to-point observations, the rotorcraft seems like a better solution.